Alright guys, so today we're going to talk about just an introduction to Calculus 1. So this is a really short section. There's not a whole lot to it. We're just going to give some kind of big picture ideas about where we're going this semester. So first we're going to do a little bit of comparison, things you can do with pre-calc versus things that you need calculus to solve. Then we're going to talk about two of the basic problems that calculus answers, and that is finding tangent lines and then finding areas of irregular shapes. So that's what we're going to talk about today. Again, pretty short lesson, but it's the first of the semester. So let's see what this is all about. Alright, so what is calculus? In one short sentence, calculus is the mathematics of change. Okay. We're going to talk about velocities, accelerations, lots about tangent lines, slopes, lots about area, and then if you go beyond Calc 1, you'll talk about volume and arc lengths and lots of more stuff. But we're going to stop in Calc 1 at area is where we get to at the very end of the semester. Okay, so you might think to yourself, well, we've talked a lot about stuff like that before in college algebra, in intermediate algebra, in pre-calc. We talk about slopes and we talk about velocity and stuff like that. But in calculus, things get a little more complicated. The main difference here is that in calculus we can talk about, say, a situation where a velocity is changing, or acceleration is changing, or slope is changing, and in pre-calc, you were pretty limited as to what you could do with a velocity function or a acceleration function and stuff like that. With slopes, you were limited as to what when you could find slope. You could find slope of a line. We've known how to do that, probably since junior high. But what about the slope of a curve at a point? That's kind of where we're going in a little while. Be able to find these characteristics as things are changing. So calculus is more dynamic, is how the text puts it here, whereas pre-calculus is a little more static. Okay, so let's see here. I've touched on a couple of these, but in pre-algebra, or excuse me, in pre-calculus, you could talk about distance functions. Distance equals rate times time, and you could talk about finding distance traveled and time and speed. But if you think about it, in all those word problems you probably worked, the speed was always constant. The speed didn't change, because if the speed was changing, you needed calculus. And like I said earlier, in pre-calculus, you could find the slope of a line all day long. But if you have a curve, you never have dealt with that, most likely, in pre-calculus. And there's more examples here. If you want to be able to find the area of some shape, well, with pre-calculus methods, you know how to find the area of a circle, hopefully, of a rectangle, maybe a trapezoid if you remember that formula. Maybe some volumes of like a sphere, maybe some surface areas, maybe if you remember those formulas. But what if you have just some really irregular shape? How would you go about finding the area of an irregular shape, or the volume of an irregular shape? That's where calculus comes into play. And here, very important, is kind of in the middle of the slide here, is the thing that is the basis for calculus, and that basis is called the limit process. Okay, whether we're talking about what's called differential calculus or integral calculus. Those are the two main branches of stuff we're going to talk about this semester. It's the limit process that's the basis for both of those. So chapter 2, which this lesson is the start of, is all about limits. Now, we're not really going to get a whole lot into it today. We'll talk about some big picture, kind of like what a limit kind of means in a big picture way, but we won't get into the nitty gritty today. But limits are very, very important. Okay, and again, the limit is the thing that takes you from pre-calc to calc. Okay. Now, let's see here. Here's a pretty good warning while we're here. There are a lot of formulas in calculus. Okay, you're going to have a whole list of derivatives to memorize here soon. Toward the end of the semester, you're going to have a whole list of integrals to memorize. There's a whole lot of formulas. There's lots of theorems you're going to memorize. But it's really important here to have a big picture conceptual understanding of what's going on. If you think that you're just going to be able to memorize a set of derivatives and then a set of integrals and then call it a day, it's not going to work out well. So we really need to think about big picture. Now, it's important to memorize those things so that they just become second nature and that you can then really put the brain power into looking and finding that big picture, as opposed to spending all your energy just remembering those formulas and trying to work with those formulas. If you practice a lot, they'll become second nature, and then you can free up all that space in your mind to think about big picture ideas. So there's going to be a lot of formulas and a lot of things to memorize, but big picture is what we're going for here. With practice, it'll all come. So as long as you're willing to put in the time, I'm confident that all you guys can do well. As long as you're willing to put in the time, day after day, week after week, and that's what calculus takes. All right, so let's just look at a few specific examples here. So here on the left we have a picture. So it's a curve, and if you're trying to do some sort of analysis, you could certainly evaluate the function f. You can evaluate it at c and see what the value f of c equals. Assuming, like in this case, f of c exists, it looks like. However, in calculus, we are certainly concerned with finding f of c in many cases, but we're more concerned with what is the behavior of the function close to c. For instance, what's going on to the left of c and what's going on to the right of c. So what's the trend? Okay, that's what we're talking about. In many cases when we're talking about limits. What's the behavior of the function around the x value x equals c? So this is an x value down here, and the trend is that there's this nice smooth curve going up and going down. So here, the limit as x approaches c actually is going to equal f of c. Okay, we'll talk extensively about that in the very near future. Here's some more examples. In pre-calc, you could find the slope of a line all day long. That's a formula you've known since probably junior high. In calculus, though, we're going to talk extensively about finding the slope of a curve at a specific point. You may not be so familiar with this term, but a secant line, that's just a line that passes through 2 points on a curve. You might remember that from geometry, talking about maybe a secant line of a circle. But anyway, it's something we're also going to talk a pretty good bit about here, probably in section 2.2. Actually, in 2.1 in the homework, we have a couple examples. I'll probably work an example before I wrap things up today. But you can find the equation of a secant line, just using the point slope form, the slope formula, pre-algebra type stuff. But if you want to find the tangent line, now what's a tangent line? A tangent line is a line that intersects a curve that just barely touches a curve at a single point. Well, it can touch. We say it can touch the curve at a single point in a certain small neighborhood. Because if this curve was extended maybe upwards like this, that blue tangent line would intersect it again. But in the neighborhood, right where my cursor is, the blue tangent line intersects the black curve at exactly 1 point. We can talk about in pre-algebra, average rate of change. Like all those word problems you worked, where train A leaves New York and train B leaves Boston. What time do they meet? If one's going this many miles an hour, the other's going that many miles an hour. You're assuming that the trains are at time 0 and beyond traveling at a constant speed. That's not real life. In real life, the train has to speed up eventually, reach max speed, and both of those trains have to do that. So in calculus, we can talk about how objects behave when the velocity is changing. Okay, when they're not traveling at a constant speed, which is how real life works. Okay, let's see a few more examples here. We can do things. We'll talk about this a lot. Finding the maximum of a graph. Okay, now you did this a little bit, perhaps. Let's see, maybe in college algebra, maybe pre-calc. You could find, say, the maximum or minimum of certain types of functions. Like, let's say you had a quadratic function. Well, we know that a quadratic function has a graph that's parabolic. And if the leading coefficient is positive, then the parabola will be opening upward, and so the vertex will be a minimum. Or if the leading coefficient is negative, then the parabola will be opening downward, so the vertex will be a maximum. But if we were only dealing with parabolas, that would be fine. But in calculus, we're going to talk about finding the maximums or maybe minimums of just any number of functions, nothing really specific. So, in beyond Calc 1, you'll get into three-dimensional calculus, and you'll be talking about tangent lines to spheres or vectors and stuff like that. Okay. Toward the end, now this is getting into integral calculus here. Towards the end, like I talked about earlier, you know how to find the area of a rectangle, but what about that area right there? There's no formula you have just to find that area. Okay, so you'll need what's called integration, definite integration, to find the area of that shaded portion there. Okay. And then this gets a little bit beyond Calc 1. If you want to find the center of a rectangle, well, if you remember from geometry class, the center of a rectangle is the intersection of the diagonals. That's no big deal as long as you remember that. But if you want to find the center of mass of of an oddball shaped region, the centroid, you'll need calculus for that. Okay. If you want to find the length of a segment, oh, that's just your distance formula, right? But what about arc length? That's a little different. So that's actually we're not gonna cover that in Calc 1. That'll be beyond Calc 1. But that's something you would that's something that calculus will eventually cover. How do you find the distance there? Okay, we can't use just the regular distance formula because that only works if it's a straight line. And here's a few more examples here. These are all three-dimensional, so this is beyond Calculus 1. We won't spend too much time here. Okay? Let's talk about two main problems. The first main problem is the tangent line problem. This is kind of like the what differential calculus what we spend a lot of time in differential calculus talking about. This is me the first half of the class, the tangent line problem. Okay, so if we want to find a tangent line, so here this blue line here is the tangent line to this black curve. Okay, and I'll show you in a few minutes how we would go about estimating that tangent line using secant lines. But this is one of the major classical problems that calculus solves. You have the area problem and the tangent line problem. So first, let's talk about the tangent line problem. So let's say we have 2 points on a curve. Okay? So let's see. We have this point over here. It's C, f of C. And then if we move a little bit to the right, that would be C plus delta x. If this little distance right here, this horizontal distance is delta x. Now, if you remember, sometimes we have the slope formula labeled as delta y over delta x. That's the change in y over change in x. Delta, when you see a capital delta like that, just means a small change. So delta x is just a small change in the x values. So we have, here is the point C, comma f of C. If we move to the right, that x value right here is C plus delta x. So f of C plus delta x would be the y value. So here's Q has the coordinates C plus delta x, comma f at C plus delta x. Now the thing is, that is a secant line. But let's say I wanted to find a tangent line at this point right here. What I could do is slide this point closer and closer and closer to this point on the left. That is, I could make delta x smaller and smaller. In fact, let me show you how this works. I pulled up a graph earlier. So let's turn that off. No, let's leave that. Let's turn this off and turn this off. Okay. So here, this red curve right here, that's just this function right here, 1/2 x squared, 0.5 x squared. It's just a parabola. I've zoomed in. So there is the parabola. And I have 2 points. So I have purple point and I have a green point. Now I want to find the tangent line to this red curve at the purple point, and let's see, which one was it? Not that one, it was this one. That purple line is the tangent line to that red curve. So like if I keep zooming in here, it gets really close, and I'm so zoomed in here, look at the scale. The scale is barely changing, and it just touches at that bottom side of that red curve. So that is the tangent line. So here's maybe a big picture to see what a tangent line is. This purple line passes through, intersects the red curve at exactly 1 point. Now, so in the coming weeks, we'll learn exactly how to find that purple curve. Okay? But what about if we didn't have calculus, like we don't right now, and we wanted to estimate that purple line? I said curves a second ago. Purple line. I want to estimate that tangent line. Well, what I can do is, let's see here. I can introduce this green line. Now notice what's going on here. The green line passes through the point in question, the purple point, and another point on the red curve. So notice here that that green line is kind of similar to the purple line. I mean, it's not exactly it, but it's not too far off. But watch what happens as I move the green point closer to the purple point. Watch how the green line will get closer and closer and closer to the purple line. So watch what's going on here. Oh, wrong one, sorry. Moving the wrong thing. I moved all of them together. I need to just move this. So let me move that back to where it was. I think it was about right there. Sorry, okay. I need to move just the green point. So watch here as I move it closer and closer and closer to the purple point. So notice there, they just completely coincided. That is, watch, see, now they're almost the same. And then when the purple and the green dots coincide, they actually are the same. So see how I move it further away, the green line, the slope of the green line is changing completely. But as I move it closer and closer, those two slopes are getting closer and closer together. So this is exactly what I was talking about just a moment ago. Okay? So let's say this is the point where I want to find a tangent line. What I can do is find a secant line. I can put a point on the curve where the x value, so where I was talking about delta x's just a little bit ago, so it looks like, let's see, so that is x, the x value of my purple point is 0.6. The x value of my green point is 1.2. So I would say the difference in those x values is 0.6. So delta x is 0.6. And if I keep making delta x smaller, see this h value over here, that's like my delta x. So delta x is 0.55. Then delta x is smaller, 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 smaller. As delta x gets smaller and smaller, those two lines get closer together. That is, as delta x gets closer to 0, the secant line gets closer and closer approximation to the actual tangent line. That's kind of like the limiting process. The secant line's getting smaller, smaller, smaller. Excuse me, not the secant line. Delta x is getting smaller, 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 all the way to 0, and then you have actually found the tangent line. That's what the tangent line problem is all about. How do you find a tangent line? You use secant lines to approximate it. And as the secant line, the x value of that other point gets closer and closer and closer and closer and closer to 0, to the original x value. So my original x value of the point in question is 0.6, and as my other x value gets closer and closer and closer to it, that is, we get better and better approximations of our tangent line. Oh, let's look at another example real fast. So let's say sine x. Let's see if I just, hope they don't break this entire thing. Oh, not capital X, lowercase x. Alright, let's see here. Oh, let's move this a little bit. Let's move it right there. So there is my my function sine x, and I'm going to look at the sine of 1. Okay, so let's see here. See as I move, as I move my other point. So the purple line is the tangent line of sine x when x equals 1. Okay, but let's see as I move that green point closer and closer. See how the green line looks very dissimilar to the actual tangent line. So my green secant line is very dissimilar to my purple tangent line. So my x value of this point right here is 2, but notice, so delta x right now is 1. The difference between my two x values is 1. But as the difference between my two x values gets smaller, that is, delta x gets smaller, the green line becomes a better and better approximation of the purple line until they finally coincide. That is the limiting process. Notice there's nothing special about me coming from the right-hand side. What if I was on the left-hand side? So notice now my green dot has the coordinates 0, 0, and delta x is still equal to 1 because the distance between my two x values is 1. My x value of the purple point is 1. The x value of my green point is 0. The distance between those two x values is 1. So as that distance decreases, notice the green line again becomes a better and better approximation of the purple line until it's not an approximation anymore, it's the actual tangent line. That is the gist of the tangent line problem. That was one of the major problems that calculus, that differential calculus, the first thing we're going to study, what that solves. Okay, we will talk and we'll do some more. I actually have a video, have already done a video tutorial about a problem doing this exact same thing. So check it out. It's also in the Calculus 1 playlist. So let's go back to the PowerPoints and see what's going on here. Okay, so we've already talked about this. Now let's talk about a little formula. Okay. If we have 2 points, so here's our 2 points, C comma F of C, C plus delta x, comma F at C plus delta x. What if we used our slope formula on those 2 points? Remember, with your slope formula, that's y2 minus y1 over x2 minus x1. If you just let label your points x1, y1, x2, y2, apply the slope formula, you get this right here. So here we're labeling this x2, y2, x1, y1. Then we simply apply the slope formula, and you get f of c plus delta x minus f of c over c plus delta x. That's x2 minus x1. Simplify it slightly, and there is the slope of your secant line. And as delta x gets smaller and smaller, we notice that's how we got a better and better approximation of our slope of the tangent line. We had the green line got better and better, closer and closer to the purple line. This right here will look very familiar coming up very soon here. Okay? Chapter 3 will be a lot of things that look just like this, but we can leave it there for now. Alright, this is exactly what we talked about, moving that point closer and closer and closer to here to get a better and better approximation of your tangent line. Okay, what about area? So this is the other major problem that we're going to talk about in Calculus 1. So that first tangent line problem, that's all about differential calculus. The area problem, that's integral calculus. So again, the driver of all this is the limit process. That is, like before, we were letting the difference in the x values get smaller, 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 smaller. That was the limiting process. We're going to do a similar thing here with the area problem. That is, we're going to let the width of some rectangles get smaller, 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 and you'll see how that helps us find area. Okay? So, with precalculus, if you're given a situation like this, you need to find the area under this curve, this kind of pinkish shaded area. There wouldn't really be any way to do it. Okay? Now you could get an approximation, I suppose. I mean, you could say, like, try to fit, a rectangle, maybe a rectangle with a height about, maybe like right here, and a width of b minus a. And then you can say, yeah, that's pretty close. But that's the best you can do. But here is what we're going to do in calculus. What if we divide up the x-axis with, maybe 4 times, maybe 8 times, and then draw rectangles above those mini sub-intervals. Okay? And stop the rectangles according to some rule. Notice here, we stop the rectangles when the left-hand endpoint of each sub-interval intersects the curve. So here's one rectangle. We found the height of the rectangle directly above the left endpoint. So go here. Here's the left endpoint of my second rectangle. Go up till I hit the curve. That's the height of my second rectangle. Here's the third rectangle. Use the left-hand endpoint, and there's the height of that rectangle. Here's my fourth rectangle. Use the left-hand endpoint. Go all the way up. There you go. Okay, that's going to be called the left-hand sum. Eventually, we'll talk about this in great detail. Okay, because we're using the left-hand side of those rectangles to find the height of the rectangles. So notice some of them went slightly above. Most of them were below. Whether the rectangle ends up being above or below the curve depends on whether the function's increasing or decreasing. Notice here the function's increasing on this interval, and so that's the rectangles tend to be under, but the function's decreasing on this interval. So even though we're using the left-hand endpoints of the rectangles, sometimes they're below the curve completely, other times they're above the curve. And I think we can all see pretty clearly that as we increase the number of rectangles, the approximation for area gets better and better. Right here, there's a lot of error. For instance, you miss this little section, you overestimate here, and you miss this big section. But when we used 8 rectangles instead of 4, I think the error gets smaller. Now you have more places where there's error, but the error in general will be a lot smaller. And I think you can see where we're going here. If we keep increasing the number of rectangles, eventually the error will get very, very, very small. That is, if we increase the number of rectangles, which means the width of the rectangles is getting very small, eventually we will find the exact area via the limit process. So we let the number of rectangles go off to infinity. We have 10 rectangles, then 100 rectangles, then 1,000 rectangles, then 10,000 rectangles. Eventually, you'll get, if you let the number of rectangles go off toward positive infinity, you will get the actual area under the curve. Okay? And that is going to be the big idea of how we find the definite integrals. And that's going to be chapter 5, toward the end of class. Now, let's look at maybe another graph. Let me see if I have one saved here. It's actually the exact same function, 1/2 x squared. So if I want to look at the area, let's say between a equals 0 and b equals 5. So my 2x values are 0 and 5. I'm using, let's see, to start with, let's see the worst case scenario. Let's say I use, actually I need, since this is a left-hand sum, notice here you don't see anything. That's because with a left-hand sum, I'm using the height that's above the left-hand endpoint of my rectangle. Let's say I only have one rectangle. Well, the height would be f of 0. But what's f of 0 when this is our function? It is 0. So there is essentially a rectangle of 0 height. The width of the rectangle is 5, but the height of the rectangle is 0. So that's a really terrible approximation. But let's see here as I increase the number of rectangles. So now there's, let's say, it's hard to do. Let's say there's 3 rectangles. Again, you may say I'm wrong, but there is 3 rectangles. It just happens that one of those rectangles has a height of 0. Okay? So that's, I mean, a pretty bad approximation still, but let's increase the number of rectangles. There's 10 rectangles, so each one of these rectangles is, since this is an increasing function over the interval from 0 to 5, all of my rectangles happen to be below the curve. Again, if you're using a left-hand sum and the function's increasing, then it's going to be what's called a lower sum. So this underestimates the actual area. So the error is all these little spots that aren't shaded, because I want everything below the curve from 0 to 5. So here's missing, all these little spots are missing. But watch what happens to all that error as I increase the number of rectangles. There's 50 rectangles. I think we can all agree that that's a better approximation of the area under the curve between 0 and 5. And let's see, I can keep going here. I mean, eventually you won't be able to tell the difference. I mean, that is, if I zoom in, little bitty errors. There's 500 rectangles. Little bitty errors. But if I zoom out, I can't even tell there's any difference. That's a pretty darn good approximation. Okay? I have to zoom in really, really close to see there's lots and lots of little bitty errors. Okay? So there we are. That is what we are going to do in Chapter 5. Now, it's, you know, I hope that's pretty easy to understand as far as what's going on there. That is, we are using the limit process to increase the number of rectangles. Now, we haven't talked about the mechanics of how to do that mathematically, but it's you know, that's one of those things we're gonna use all throughout the semester. So again, I'm starting at one rectangle and using the limit process to increase the number of rectangles, practically here until 500, but it, you know, mathematically we'll increase it to an infinite number of rectangles. Again, what's happening to the width of those rectangles as you increase the number? The width of each rectangle is decreasing. So the width is decreasing, the width is getting smaller, 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 closer to 0 as the number of rectangles increases. Okay? So that is the two main you know, classical problems that we tackle in Calc 1. We tackle the area problem, like we're talking about here, and we tackle the tangent line problem, which is what I talked about a little while ago, trying to find the tangent line of a curve at a specific point. Because if you're talking about a curve, the tangent line is always changing. Always changing. So the slope of the tangent line is different, generally speaking, at different points. So you have to consider what's going on at a specific x value. And we're going to talk about that extensively a little bit in Chapter 2 and then extensively in Chapter 3. So if you have any questions, feel free to ask. Again, I'll do these you know, shorter lessons. So if you guys miss class or if you want to revisit the topic, you can always do that when you're at home, when you have a little more time to review what we did in class that day. All right, see you soon. Have a good one. Bye-bye.